Hello everybody, my name is Romy and I will present you our work on constraint-based software diversification against code reuse attacks. Software development today is based on uniformity, where end users execute identical binaries. However, this facilitates large-scale attacks. For example, assume multiple users running identical binaries, then an attacker is able to design an attack against this binary and successfully attack all these users. However, if the users run different binaries, then the attacker will not be able to successfully attack all the users. So our approach is to generate a large number of variants that are functionally equivalent but have different implementation. And at the same time, we want to control the quality of the generated variants with regards to the execution time or code size. In this work, we use a constraint-based compiler backend, in particular Unison, that takes as input the function in C code and outputs the optimal implementation in assembly code. Unison implements two low-level transformations, instruction scheduling that uses the cumulative constraint, and register allocation that uses a geometric packing constraint. Here we have the factorial function as example that, given as input to Unison, will generate the optimal solution that corresponds to an implementation of the function in assembly code. However, there are other solutions to the model that are not necessarily optimal. For example, here we have another implementation which has different register assignment for this operand, and the last three instructions are delayed by one cycle, resulting in an OP operation. So our approach is to generate a large number of variants that correspond to solutions to the constraint-based compiler backend. And to do that, we use a form of large neighborhood search around the optimal solution, which we also use to control the quality of the generated variants. Our results show that large neighborhood search is a promising approach for finding diverse solutions in CP. We studied the trade-off between quality and diversity and show that our approach to diversity by construction is effective against code reuse attacks. If you're interested in our work, please watch our full video or read our paper. Thank you. Hello everybody, my name is Romy and I will present you our work on constraint-based software diversification against code reuse attacks. I will start by introducing the problem that motivates our approach. I will continue with the description of a constraint-based compiler backend that we use in our approach to diversity by construction, and finally discuss the evaluation and the security impact of our approach. Software development today is based on uniformity, where end users execute identical binaries. However, this facilitates large-scale attacks. For example, assume many users running identical binaries, then an attacker is able to design an attack against this binary and successfully attack all these users. However, if every user runs a different binary, then the attacker will not be able to successfully attack all the users. So our approach is to generate a large number of variants that are functionally equivalent but have different implementation, and at the same time we want to control the quality of the generated code with regards to the execution time and code size. There is a lot of research in compiler-based randomization. However, most of these approaches do not consider the quality of the generated variants. Among those that do that, there is an approach that performs only transformation with zero execution time overhead, and another approach that uses profiling for controlling the execution time of the generated variants. There are a few search-based approaches, like Super Diversifier that does not have an accurate cost function, and another approach based on program synthesis, which is work in progress. In this work, we use a constraint-based compiler backend, in particular Unison, that takes as input a function in C code and outputs the optimal implementation in assembly code. The decision variables of the model are the issue cycles of each instruction, the instruction implementation of each instruction, and the processor register for each operand. The constraints of the model are the program semantics, the hardware description, and the program transformations. In particular, Unison implements two low-level transformations, instruction scheduling that uses a cumulative constraint, and register allocation that uses a geometric packing constraint. The optimization goal is execution time and code size. Here we have the Factorial function as example, which given as input to Unison, will generate the optimal solution that is an implementation of the function in assembly code. However, there are other solutions that are not necessarily optimal. For example, here we have a different solution that has a different register assignment for this operand, and the last three instructions are issued one cycle later, resulting in an op operation. So our approach, diversity by construction, generates a large number of variants that corresponds to solutions to the constraint-based compiler backend, and at the same time we're able to control the quality of the generated code by using the optimal solution provided by Unison. Diversity is a known problem in CP, with max diverse case A being the problem of generating case solutions that have maximum pairwise distance. There is an exact algorithm, however it is not scalable, so we'll look into the incremental algorithm for approximating the problem. This incremental algorithm adds one solution to the set of solutions at every iteration by maximizing the distance to the already found solutions. Here, the distance function measures the difference between two solutions. However, this approach is not scalable enough. To improve the scalability of this application, an application that requires a large number of variants, another approach replaces the maximization step with a local search. DivCon uses large neighborhood search, that is a meta-heuristic that defines a neighborhood through a destroy and repair function. It defines the relaxed rate, that is the probability that the assignment of a variable is destroyed. We use an incremental algorithm similar to the ones we saw previously, but instead of the maximization step, we use the next solution of LNS by relaxing the previous solution. Since we do not maximize the distance, we need to add a lower bound to the distance from the solutions. To control the quality of the generated code, we can use the optimal solution O and constrain the cost function to be within a percentage P of the optimal solution. The distance measure, as we said before, is a function that measures the difference between two solutions. For our problem, we define two distance measures. First, the Hamming distance, that is the Hamming distance between the issue cycle variables. In the example solutions of the factorial function that we saw before, the Hamming distance will be 3 because the last three instructions of the second implementation are issued one cycle later. The second distance we define is the Levenstein distance, that is the edit distance between the instruction schedule of the two solutions. Each instruction is analogous to a letter in the edit distance between strings. Here, the two implementations have a Levenstein distance of 1 because an op operation is inserted in the instruction schedule. To evaluate DivCon, we implement our algorithm in G code. We use MIPS as the target architecture because MIPS is an important architecture within embedded systems. We use 17 small functions as benchmarks and use execution time as a quality measure. The experiments aim at generating 200 variants. To compare the different algorithms and configurations, we use the pairwise distance as shown here. The first question we want to address is what is the scalability of the distance measures in generating multiple program variants? In the table here, we show the two distance measures, Hamming distance and Levenshtein distance, and for each of these measures we list the time in seconds it takes for generating all the variants, and under num the number of the generated variants. We skip the execution time in cases when we have a timeout. From the results we can see that the Levenshtein distance is not scalable to a large number of variants, whereas Hamming distance is able to generate a total number of variants within a few seconds. Our approach requires the generation of a large number of variants, and therefore we cannot select the Levenshtein distance. Our second question to address is how effective is LNS at achieving high diversity with low time overhead. Here we compare three algorithms: incremental max diverse k-set algorithm, random search, and our approach large neighborhood search with a relaxed rate of 70%. For each of the algorithms, we show the pairwise distance d and the time in seconds it takes for generating 200 variants. The values in bold correspond to the best values, namely the highest pairwise distance and the minimum time t. We can see that max diverse k-set algorithm generates the most diverse solutions in the cases where it is able to generate all the solutions. However, the algorithm is not able to generate the total number of variants within the time limit for most of the benchmarks. Comparing random search and large neighborhood search, we see that random search is more scalable but generates solutions with low diversity. Our algorithm generates high diverse solutions compared to random search, whereas the time overhead is still below 5 seconds. So we can conclude that our algorithm is a promising approach for generating highly diverse solutions with low overhead. Our next question is what is the relation between code quality and code diversity? Here we saw different values of the optimality gap and the pairwise distance and the number of generated variants for each of these values. As expected, increasing the optimality gap improves the diversity of the variants. We can also see that the rate of change is reducing, and thus the optimality gap of 10% can give us quite high diversity. So our approach is aiming at using diversification as a mitigation against code reuse attacks. So code reuse attacks, and in particular we'll talk about return-oriented programming and jump-oriented programming, use existing code to hijack the control flow of the target program. In particular, they exploit a memory vulnerability to insert data in the program memory to redirect the execution to existing code snippets that form the so-called gadgets. A chain of gadgets constitutes an attack. So the idea is that by relocating or changing the code of the gadgets in a program, we can break the functionality of the attack. To evaluate how effective is our approach against code reuse attacks, we want to measure how many of the gadgets are shared among variants. In this table, we show for different values of the optimality gap, the percentage of pairs of variants that do not have any common gadgets, the percentage of pairs of variants that have 0 to 10% common gadgets, the percentage of pair of variants that have 10 to 40% of the gadgets, and finally those that have more than 40% of the common gadgets. The values in bold correspond to the modes of the histogram. So ideally we would like all pairs of variables to share no gadgets and thus have larger values under the first column here. The results show that with a higher optimality gap, the better the mitigation effectiveness of our approach. However, the difference is larger between 0 optimality gap and 10%, whereas increasing more the optimality gap has reduced effect on the percentage of common gadgets. So we can conclude that within an acceptable optimality gap of 10%, we get effective mitigation against code reuse attacks. So to conclude, our contributions are that we propose a CP-based technique for compiler-based, quality-aware software diversification. We show that LNS is a promising technique for generating high diverse solutions efficiently. We quantify the trade-off between code quality and diversity and demonstrate that DivCon mitigates code reuse attacks effectively while preserving high code quality. As future work, we plan to refine the distance measure to include register allocation and improve the scalability of DivCon for medium-sized programs. Finally, we would like to acknowledge the critical contribution of Christian Schulte at the beginning of this work, which he could not unfortunately continue. If you are interested in our work, please read our paper. Thank you.